for the introduction, and good morning to you all. On behalf of Qenos Alcataf, proud partners of the 2018 ARMA Masterclass Series, we extend a warm welcome to everyone at this event. So today, in our presentation, we'll be looking at some of the common pigments that are utilised in rotomoulding and how they alter the behaviours of polyethylene. And we'll try to shed some light on why certain colours behave the way they do. So we need colours to enhance our products. But what else do colours do? So before I continue, can I just get a show of hands to see who's representing moulders in the industry today? It's a great turnout. Very good. So these are some of the comments our moulders have shared with us over the years about their observations with the different colours. If I cook heritage red above 185 degrees, it dies. Smooth cream is hard to mould. Heritage green turns white in the sun. Heritage red and green rip off my mould release. And beige lasts a long time at the mines. So to gain more information about the colour performance, ARMA conducted a survey of the moulders. The survey was focused on the following points: cook time, impact strength, shrinkage, warpage, mould sticking. Now the first 5 ones are to do with the moulding process itself. The last 3, fade resistance, tendency to crack and lifespan, are to do with its time out in the field. The survey found that white and off-white colours take a long time to cook and have poor impact strength. So, as we can see from this slide, the 2 tables, we'll focus on the cook time first. Based on the survey, we found that smooth cream, merino, white and beige had a long time to cook, whereas blue, heritage green, heritage red had a short cook time. It also found that smooth cream, white and heritage green had a poor impact strength, whereas black, river gum, grey and mist green exhibited good impact strength. So this raises a question. Do white and off-white colours need to be cooked longer to attain good impact strength? White and off-white colours stick harder, but shrink and warp less. So here we can see that the survey showed that smooth cream, white and light colours had low warpage, whereas heritage green and dark colours exhibited high warpage. It also showed that smooth cream, white and light colours once again had low shrinkage, and heritage green, dark colours and blue exhibited high shrinkage. So these findings show a strong relationship between these 2 properties, warpage and shrinkage. With mould sticking, we saw that smooth cream, white, beige, heritage green and heritage red exhibited high mould sticking, whereas black exhibited low mould sticking. So what we know is that these findings raise a few questions. Do white and off-white colours warp less because they stick more? Well, the longer that the sample sticks to the mould, the better it can take the mould shape, is what we understand. It raises another question. Heritage green is sticky and also has high shrinkage and warpage. Why is this? We'll endeavour to answer this further on in the presentation. Heritage colours tend to fade, and along with blue, they tend to have a shorter lifespan. So based on the survey, we found that heritage green, heritage red, red, yellow and orange exhibited a faster rate of fading, whereas beige, black and the lighter colours exhibited a low rate of fading. It also showed that heritage green and blue had a high tendency to crack in service, whereas beige and mist green had a low tendency to crack. With regards to lifespan, heritage green and heritage red, including blue, had a short lifespan, and beige, black, river gum and light grey exhibited long lifespans. So beige, black and lighter greens generally perform better than the other colours based on these properties. So why do the different colours behave differently? So let's have a look at what the colours are and what they do to the properties of polyethylene. Now, colours are made from pigments. They may be single pigments or they may be mixtures. Pigments can be mined or they might be made in a factory. Now, the chemical structures may be simple or they may be complex. So how do the pigments get into the coloured polyethylene powder? So here what we have is some premium Qenos polyethylene, the pigments, and any special ingredients that are required. The extruder melts the polyethylene and mixes the pigments and the other ingredients to give us a master batch. So the master batch typically contains 50 to 70% of the pigment. Now the master batch is added at a rate of 1 to 2% to premium polyethylene and passed through a heated extruder to produce the coloured compound. Now this coloured compound is then ground into powder using a mill, and this is how we achieve our end product, polyethylene powder. Now there aren't a lot of pigments that can be used in polyethylene for rotational moulding. There are some important criteria that they must meet. The first point, they must retain colour at high moulding temperatures. Now this first point knocks out a lot of the pigments at play because they cannot stand the heat of long exposure times during the rotomoulding process. They must also be fade resistant outdoors. They must not bleed out onto the mould. They must be suitable for water and food contact where required, and they must not contain heavy metals. They must be low in cost and be effective at low addition rates. Now these are some of the pigments commonly used in rotational moulding. On the left, we have the pigment type, and on the right we show the finished product that these pigments typically go into. So we'll just go through them. Titanium dioxide white is utilised in white, beige, smooth cream and grey. Carbon black is utilised in black, grey and monument. Iron oxide red is typically used in heritage red. Phthalocyanine blue is utilised in mountain blue. Ultramarine blue is used in storm edge. Chrome titanate brown is used in bronze olive, jasper and monument. Chrome green, typically used in mist green and river gum, and phthalocyanine green is typically used in heritage green. So to study their effects on polyethylene, we compounded them with Qenos Alcatuf 711 UV powder at a rate of 0.3%. The 711 UV being Qenos' premium rotation moulding grade and 0.3% being a typical loading level. So the first thing we noticed is that the pigments absorbed light to different degrees. So what we did here was we measured the amount of light transmitted through a 5mm thickness compression moulded plaque using a light transmission meter. And there's some background information. The light transmission level is linked to the effects of algae growth, where low light transmission prevents algae growth in water tanks. Now we need to mention here that for presentation purposes, we've actually utilised yellow to represent the unpigmented natural material. Now the results show that natural gave us a 44% light transmission. It also showed that titanium dioxide white is not a good absorber of light. So what we needed to do was increase its addition rate from 0.3% to 1.5% to achieve a lower light transmission level of around 1%. Now this is also done in industry. And as we can see from this data, the darker pigmented materials gave us low light transmissions as we expected. The pigments did not affect the impact strength of compression moulded samples. So here an instrument impact test was conducted on 5mm thickness compression mould samples, which allows us to measure the energy required to break. And as we can see from this slide, there is no considerable difference between the various pigments tested. They're all on par with each other. The pigments did not affect the rigidity. So this test measures the flexural modulus of a sample. It's a bending test. And again, the results show no considerable differences between all the pigments tested. Phthalocyanine blue and green increase both the melting and freezing temperatures. So as seen in these graphs, phthalocyanine blue and phthalocyanine green showed higher melting temperatures and freezing temperatures compared to the other pigments tested. Now this is because these two pigments nucleate. They act as nucleating agents. They act as a seed for crystals to form early. Now nucleation is the same effect that is used in cloud seeding to make it rain, where you introduce small particles for crystals to form. And in cloud seeding, these particles are ice crystals that form, as a comparison. So to demonstrate this, what we have here is a mixture of natural and blue powder at 200 degrees under high magnification. Now you can see the surface through the natural material, it is clear. And you can also see some shiny bits. Those shiny bits are scratches on the internal surface of the mould. So we'll play a video here. So here we see the material is now cooling down from 200 degrees Celsius. And we can see that the phthalocyanine blue material has frozen first. And we can still see through the natural material because it's still in the molten stage. Now, as we cool down further, the natural has solidified and become opaque and blocked out the mould completely. So here what we're showing is that phthalocyanine blue exhibits a high freezing temperature, which means it freezes first. Blending materials with different freezing points results in orange peel on the inner surface of a moulding. So for anyone who has blended different powders, this is a major reason for orange peel effect. What this photo shows is an image of an internal surface of a moulding made with a 50-50 mix of natural and phthalocyanine green powder. The larger bits of green are the phthalocyanine green particles, and the shinier, darker bits are the natural particles. Now the natural shrinks after the green to form the valleys. So here what we've identified is one of the major causes of orange peel, which is caused by the effects of shrinking, which is caused by the different freezing points of the pigments. All the pigments reduce the amount of heat required to take the material up to 180 degrees. So this is just one of the factors that influences how long it takes to cook a specific colour. What this slide shows is that if you put heat into a material, you don't have to put as much heat into pigmented material. Phthalocyanine blue and iron oxide red both increase the melt flow index of the material. Now this test is an indication to us that they are possibly causing and assisting in the degradation of the material at a faster rate than any of the other pigments tested. The pigments had major effects upon the rate of surface oxidation when exposed to heat. So this is where we put the material through a test of applying 200 degrees constant heat and measuring how long they take to oxidise. And again, the iron oxide and the phthalocyanine blue have had a major effect on the thermal stability and the surface degradation by failing first. What we know is that the low thermal stability may lead to poor impact strength and may also play a role on how hard things stick. Some of the pigments had a major effect upon the crack resistance. Now, this test was conducted on what we call an FNCT test. It's where a specimen is notched all the way around and a constant load is applied on it at 50 degrees Celsius with a 2% Igopal detergent solution. The phthalocyanine blue and the phthalocyanine green displayed the early failures here, once again. So this test is important because typical failures in polyethylene mouldings tend to be crack failures, and it's important to be aware of the different types of pigments used. Pigments absorb sunlight and convert it into heat. So we've laid some compression moulded samples horizontally in full sunlight. Now, we would expect the black to be the hottest, but it's a matter of how much. By using a thermal imaging camera, we can see that the black is in fact the hottest, followed by the iron oxides and the blues. The whites and the naturals, as expected, are the coldest. The different pigments generated different amounts of heat. Now, bear in mind this was conducted in Melbourne on a typically hot 23 degree summer day. We measured the temperatures of the samples across a full day, and the measure was conducted utilising an infrared pyrometer. And as we can see, the naturals and the whites were the coolest, and the rest of the pigments being much hotter, with the black being the hottest. What we see here is there's a little wave in the graphs here, and that's due to some very light cloud cover in the middle of the day that's been detected. As the air temperature increases, so do the colours. Here we have two graphs, measurements taken on 2 different days to show the different effects. Measurements were taken at 1 p.m. when the sun was straight up. On one of the days, the air temperature was at 26 degrees, and on the other, it was 34 degrees. And we can see the differences in the temperatures. On average, the white increased by about 8 degrees, and the black increased the most by 41 degrees. So this is quite a significant increase in temperature. So it's important to note this. So what happens to real mouldings during the day? What we have here is a group of mist green tanks out in the field. The side walls of tanks get quite hot in the morning and in the afternoon. So these are thermal images taken at 10 a.m, 1 p.m, and 4 p.m. in the afternoon. The air temperatures are 20 degrees, 23 degrees, and 25 degrees respectively. And we can see that the maximum wall temperatures throughout the day rising as high as 49 degrees, 43 in the middle of the day, and 53 in the afternoon. So this is a high increase in temperature compared to the air temperature around it. Full or empty makes a difference. On the left, we have the full tank at 43 degrees compared to the empty one at 53 degrees. And on the right, we can see a partially filled tank. The water-filled section is at 44 degrees compared to the empty section at 53. So what we have here is water is having a dampening effect on the wall temperature, keeping the wall temperature down. At night, things reverse. You can clearly see that the tank that is partially full. The water-filled section is higher in temp than the empty section. And we can see here that the water is still retaining the heat from earlier on in the day. "4 p.m. vertical is equal to 1 p.m. horizontal." What does this mean? So we were surprised that the side of the wall tanks got so hot in the morning and in the afternoon. So we wondered what would happen if we placed those coloured samples, compression mould samples from earlier on, vertically and measured their temperatures in the afternoon at 4 p.m. And what we found was that they got to very similar temperatures to what they reached in the middle of the day when placed horizontally. So this was just an in-house test that we thought we'd conduct. So how do the elevated temperatures affect the properties of the coloured polyethylene? So to answer this, what we did was we looked at the data generated from the previous testings and applied a working temperature to each of the pigments. Now these are estimated temperatures that the material may attain outdoors in Australasia for significant periods of time. And based on the data, the natural and the titanium dioxide white had a working temperature of around 40 degrees. The majority of the pigments were sitting around 50 to 55 degrees, and the black was the hottest at 63 degrees. To find out what happens, we tested the coloured materials at their working temperatures. So we tested for rigidity, the amount of expansion, and also crack resistance. And what we found was that solar heating results in a reduction of rigidity. Again, this is a flex modulus test. Again, it's a bending test. So the tests were conducted at the pigment's working temperatures. And the natural and the white reduced by around 40% in rigidity, as we can see from the data here. And the rest of the pigments reduced by around 60% in rigidity. So the whites and the naturals exhibited a better performance for this test. Solar heating resulted in different amounts of expansion. So here plaques were measured at 23 degrees and then at their working temperatures. And we can see that the white expanded the least and black the most. Now this test helps us understand the change in size of a moulding from day to night that may result in stress and possibly a faster rate of fatigue and possibly resulting in cracking. So it's important information for us. Solar heating has a major effect upon crack resistance. Now this is one of the most critical properties of polyethylene products, as we mentioned earlier. And here we can see that there is very good performance once again from the white pigments as they lasted the longest compared to all the coloured pigments. Now, additives can change some of the effects of pigments. So, although this was outside the scope of the study, it's important to mention that the addition of additives such as mould release additives and thermal stabilisers can change some of the effects of the pigments. So what we're trying to show here with all these findings is that when you observe differences in the moulding processes and out in the field, there are reasons based on physical and chemical properties of the material and why these may occur. And so in conclusion, there are a number of things we might conclude from this study. There are a limited number of pigments suitable for rotational moulding. Some pigments can change the melting and freezing temperatures of polyethylene. The pigments can change the thermal stability of polyethylene. They can also change the crack resistance of polyethylene and also have a change in the effective shrinkage rate of polyethylene. Pigments can change the properties of polyethylene via solar heating, and some of the effects of pigments can be addressed with additives. So this brings us to the end of the presentation. Thank you for your attention.
Thanks, Tom. Are there any questions? Hold on just one sec, Ben. We'll get the microphone over. Tom, if you come back here, I'll do this.
Hey, what kind of effects can you address with additives?
So additives, depending on what the additives are, may assist in the oxidation.
Okay.
So combating the degradation of the material during the moulding process, and also out in the field as well.
Okay, and that degradation was due to the pigment?
Degradation during the pigment and the material itself. So there's a balance between the two. So
Thanks.
no worries.
Anyone else? No?
Pigments alter behaviour of polyethylene. Why? What's the chemical, physical nature of what's going on?
That's a good question. Why do they? So what we've proven here is that they do. There are reasons why they do. We've done multiple tests to see what effects they've had. We can identify what the pigments, which types of pigments have what effects on the end product, as we've shown here. Why? There's a lot more work that's involved to go into it. There's some literature out there, which I'm happy to share with you offline, if that's okay. But yeah, so our role is really to understand what the effects are to help us understand long-term why they are affecting it. So, and there's a bit of work happening at the moment to address that as well. Pigments being quite a complex structure as well. It's quite simple and complex, yes.
Would it be right to conclude that the fellows and the iron oxide are the two components that cause some of the most stark changes?
Based on a couple of tests that we've conducted, that we've clearly shown today, iron oxide and blue do have an impact. So it's quite clear that they do. Compared to the
alternatives that you can use that are worthwhile as well.
Correct. But again, it's a balance. You've probably seen from the presentation that iron oxide and blue have some detrimental effects on some of the properties, whereas not on the others. So it's a balancing act, again, based on what the requirement is out in the field, just to get that balance right and selection right of pigments.
All right. Thanks, Tom.
Thank you.